Do you know why I like going to Dinosaur Valley State Park? So I can hunt the tracks of the chi-square tops. Oh. All right, so we're going to go ahead and we are going to compare some different groups uh, to see if there is independence between grade level and mode of transportation. So the Student Council took a survey of Cedar Ridge students to determine what mode of transportation they used to get to school. The sample is stratified by gathering 50 randomly selected students from each grade level. What conclusion should the Student Council make about the association of grade level and mode of transportation? So, based on our initial view of the table, what do we conclude? Which data point cell was most convincing to you in your conclusion? So first of all, I'm going to go ahead and count up the number of people that walk or take the bike, then the bus and dropped off, and the ones that drove. If they were the same, then each box that contains an observed counts, not a total, is called a cell. So right here, we have a cell right there. In our example, only the white boxes are the cells. The size of a table is described as the number of rows of cells, in this case 4, times the number of columns of cells, also 4 in this situation, with rows always listed first. All right. We assume independence. So our null hypothesis for this example is the mode of transportation and grade level are independent. The opposite of independence is dependence. So our alternate hypothesis is the mode of transportation depends on grade level, or the mode of transportation and grade level are not independent. What should we expect if the null is true? To determine what is expected, just look at the totals for each category. In this particular example, we know it is stratified to have equal numbers of 9th, 10th, 11th, and 12th graders. So 1/4 of each mode of transportation should be in each grade level if they are independent. So we're going to fill in the expected counts for each grade level. It is common that expected counts are not integers, so don't freak out if it's not an integer. All right, so if we have 45 walkers, then they should be evenly split here. I should have 11.25 walkers in each of these cells. If I have 39 riding the bus, I divide that by 4, and there you go. If I have 65 dropped off or shared a ride, I assume they're equally spread out among the grade levels, and then the same thing for drove. All right, so now I have all of my expected counts. Most examples do not have even splitting among categories like we did for the grade levels. A general formula for calculating expected counts is take the row total for that cell, so across, right, times the column total for that cell divided by the grand total that's in the corner. Notice you only need a row and column totals, not the observed counts to calculate expected counts. So which cell looked the most off for expected counts? So I'm going to go ahead and put in the expected counts, and you can see that on this one it looks like, oh, none of the 9th graders drove, right? So that kind of makes sense. 9th graders don't have their driver's license yet, not usually anyways. So if we're testing if observed is different than expected, then we should look at the differences of observed and expected and add them up, like we did for the goodness of fit. And to avoid getting zeros, we'll use the same technique we did for standard deviation. So we looked at the square difference. And because not all expected values are the same size, we also normalize the square difference for each expected value before adding them up. This gives us a chi-square test statistic. So basically the same statistic as we do for the goodness of fit. So we're going to calculate the test statistic for our transportation example. We had 15 in the first cell, and the expected value is 11.25. And then we take the 13, and we add them all up. But don't worry, there's an easier way to do it on your calculator. So remember, the chi-square test statistic is for categorical variable, not quantitative, categorical data. And there are different curves for different degrees of freedom. Degrees of freedom, in this case, is a little different than the test for homogeneity, goodness of fit, than the test for goodness of fit. You take the number of rows minus 1, and the number of columns minus 1, and you multiply that out to get the degrees of freedom. Remember, just like before, curves with lower degrees of freedom are more strongly skewed to the right. As the degrees of freedom increase, the skewness to the right decreases, all right? So see how it looks more symmetric on this one than, say, any of this one right here with degrees of freedom of 3. And it starts to look more symmetric like I just mentioned. Unlike the normal and students distributions, the chi-square distribution only does right-tailed tests because we don't capture direction. So conditions are, besides independence, there is the one additional condition that must be met. All cells should have an expected count of greater than or equal to 5. Usually, you only need to check the smallest expected count, which would happen when you multiply the smallest row total by the smallest column total, and then divide by the grand total. All right, so that's the easiest way to calculate the smallest expected count. So if we were to calculate the degrees of freedom for our transportation example and determine if conditions for the chi-square distribution have been met, there are degrees of freedom. Remember, we had 4 rows and 4 columns, but we subtract 1 from each, and we have 9. And then our smallest row and our smallest column were 39 and 50. We divide by our grand total of 200, and 9.7 counts is our smallest. So that's bigger than 5. We only needed greater than or equal to 5, and that's good enough. We met the counts condition. If you want to set up an observed counts matrix on the TI-84, you can use tables. Well, you can use matrices, right? So first you must set up your observed counts matrix. Press second in matrix, all right, the x minus 1, and scroll to edit and select the matrix you wish to use for the observed counts, usually matrix A. Then you're going to press enter. Type in the number of rows, press enter, and then the number of columns and press enter, and enter the observed values in each cell. First, make sure you already set up your matrix of observed counts if you want to do a chi-square test. Then press stat and scroll to tests. So there you see tests, and then we have chi-square test. Scroll to C and press enter. Select the matrix with your observed counts, matrix A. If you need to change matrices, you can press second in matrix to change them, all right? And scroll to the matrix you set up and press enter. This is normally matrix A. The calculator will automatically set up a matrix of the expected count, so you don't have to do that one yourself, all right? Scroll down to calculate right there and press enter. If you would like to see the distribution, then you can select draw instead of calculate. And you can also check the expected counts by checking the output matrix. To check the output matrix, press second matrix and scroll to edit. Then you can scroll to the matrix for the output, normally matrix B, and press enter. And you scroll through the expected values by pressing enter repeatedly. All right. Now, use the output from the chi-square test to make a conclusion about the independence of grade level and the mode of transportation for the student council. Well, see, we have a very small p-value, 3.32 times 10 to the minus 6, really 3.33. Either way, darn close to 0, all right? So with a low p-value, we reject the null hypothesis. We have sufficient evidence that grade level and mode of transportation are not independent. Now, you can also use this test for homogeneity. So sometimes we're doing independence where we check for association, like grade level and transportation. But we can also, so that's independence. We're comparing 2 samples to determine, for homogeneity, we're comparing 2 samples to determine if they look like they're from the same population. All right, so that's the difference. The steps we just did are the same for homogeneity as they are independence. The main things that does change are the hypotheses. So if, let's say we wanted to compare our 12th grade survey results against Westwood, how would we word the null and alternate hypotheses to test homogeneity? Well, in this case, we would say both Westwood and Cedar Ridge populations are similar in how they get to school. And then in the alternate, we would say some of the proportions of transportation modes are different for Westwood and Cedar Ridge. Or you could just say the distributions are different.